नमस्कार, केम छो, आदाबर्स, वेरी गुड आफ्टरनून। आप सभी का पीआरएल के अमृत व्याख्यान में स्वागत है, अभिनंदन है। A very warm welcome from me, Anil Bharadwaj, for PRL का अमृत व्याख्यान। Today is the 79th PRL का अमृत व्याख्यान, and it is the 4th व्याख्यान of the monthly series of PRL का अमृत व्याख्यान, which we started after completing our 75 व्याख्यान series. PRL Kamrit Vyakhyaan is being celebrated to celebrate the 75 years of PRL's legacy in physics and space sciences, and also to celebrate the country's 75 years of independence. Today, we have yet another very distinguished Vyakhyaan Karta with us today, Professor Gopalan Jagadeesh, who is a professor at Department of Aerospace Engineering at Indian Institute of Sciences in Bangalore. And he is going to deliver his Vyakhyaan on shocking waves, healing touch. And this is a very interesting topic, and I believe all the audience would be really interested to hear him on this topic. So we thank Professor Jagadeesh for accepting our invitation and to be with us today at the PRL Kamrit Vyakhyaan, which is also a part of Platinum Jubilee celebration as well as Azadi Ka Amrit Mahotsav. I now request my colleague, Dr. Bala, to kindly introduce today's Vyakhyaan Karta, Professor Jagadeesh, to all the people on the on the WebEx platform, as well as those who have joined us live on the PRL YouTube channel. Over to you, Dr. Bala.
Thank you, sir. It is my pleasure and honor to introduce Professor Jagadeesh. Professor Jagadeesh is the Pratt and Whitney Chair Professor since 2016. In fact, he is the founding chairman of the Center of Excellence in Hypersonics in IISc Bangalore. It was started by the Brahmas Aerospace, New Delhi. And he's a professor of Department of Aerospace Engineering since 2011. There is much more that I can go with here to introduce Professor Jagadeesh, but I'll select a few because we have short time. Professor Jagadeesh had his early schooling in the prestigious Sri Ramakrishna Vidyashala, Mysore, and his pre-university education in National College, Basavanagudi. Later, he obtained his bachelor's degree in mechanical engineering with distinction from Bangalore Institute of Technology in 1989 and master's in BITS in thermal sciences in 1992. Then he did PhD in aerospace engineering at IISc with Professor Reddy, 1998. To date, he has 25 patents on his name from various discoveries related to shock waves and hypersonic flow control. He is fellow of the Royal Aeronautical Society UK, National Academy of Engineering, and associate fellow of American Institute of Aeronautics and Astronautics. He is currently the president of the International Shockwave Institute, Japan, and the Society for Shockwave Research in India. Of course, as I said, the volume of achievements Professor Jagadeesh has, we can go on introducing a lot, but he's an excellent speaker. So I stop here with a short introduction, and so that we have more time to listen to Professor Jagadeesh. Go to you.
Thank you very much, Dr. Bharadwaj and Dr. Bala. I'll just share my screen. I hope this is visible to all of you.
Yes, we can.
Yes.
Am I audible?
Yes.
Yes.
आप सभी को मेरा सादर प्रणाम और नमस्कार। इस अमृत व्याख्यान में मुझे बुलाने के लिए स्पेशली आई एम थैंकफुल टू डॉक्टर अनिल भारद्वाज जी। मन में तो जिज्ञासा है पूरा भाषण हिंदी में दे दो, लेकिन मेरा हिंदी का भाषा ज्ञान इतना अच्छा नहीं है, इसलिए क्षमा चाहता हूँ। सो आई विल ओनली स्पीक इन इंग्लिश दिस आफ्टरनून। Friends, what I have done here is to share some of my own very intimate thought on this particular area called shock waves, which I fell in love probably a quarter century ago. And then now I am really seeing how the paradigms of this research has shifted in the last 10 years. and how we have been able to go through the entire plethora of journey, starting from the science of shockwave to the engineering solutions to the technology which would probably touch the common man at some point in time. What I have shown you are two photographs here, one taken by one of my students on the drone. And in fact, this is the iconic building of Indian Institute of Science, and you can actually see a small blunt-shaped body. This is a panoramic view. This somehow resembled a shock wave that you can actually see on the right side. When a large explosion takes place, there's actually a shock which can be captured. And the fireball goes outside the shock almost like a tower. And I think this iconic tower of knowledge of Indian Institute of Science and shockwave somehow resemble both of them. So I thought I would just share this with you on this occasion. Of course, professors are usually very lucky. They go from forum to forum talking about several of their discoveries, but in reality, it is the large body of students who actually work in the laboratories untiringly day in and day out. So before I begin, I must acknowledge several people who have actually made this happen. In fact, the number is only growing, both the lab colleagues, our international colleagues, my own startup journey. So it's been a wonderful to work with so many people. And I very early realized this. If you want to really walk fast, you should walk alone. But then if you want to really walk far, you should walk together. It is that wonderful spirit of camaraderie and collaboration and cooperation and learning together what actually makes their area stand up in the different regimes across the world. So a big thanks to my family, colleagues, students, and funding agencies before I move forward. I am in IASC. I am sure that you would have heard the story of IASC umpteen number of times. But then, being born and brought up in Mysore, I thought that this is the right occasion to say my humble pranams to the founders of Indian Institute of Science. Many of you would have heard about the iconic letter written by J.N. Tata to Swami Vivekananda. In fact, both of them seem to have met during that famous journey of Swami Vivekananda to Chicago when he went there for the World Parliament of Religion. And it appears, just to cut the long story short, Swamiji seems to have asked J.N. Tata, what brings you on this journey? J.N. Tata seems to have remarked that I am going to the Western world to fetch steel making technology. This Hindu monk could have told him, Westerners may give you technology, but then who will teach you material science? And the conversation goes, and J.N. Tata already had firmed up opening an institute on ancient aesthetics. But then after this interaction, it becomes so clear that he wanted to have an institution for science and the ancient aesthetics. And that's why people say thoughts are so powerful, because both J.N. Tata and Swami Vivekananda were not alive when IASC was formally formed in 1909. But I am not sure how many of you know this wonderful lady that I have shown you in a portrait here, because history has not been very kind to such a noble soul. She is none other than Maharani Kemparajamani Vani Vilas Sannidhana. That is her full name. She is called Kemparajamani. She was actually mother of Nalvadi Krishnaraj Vadayar. When IASC was being discussed after J.N. Tata, when he passed away, he divided his property into two parts. Even today, we get rent from some of the properties that are there in Nariman Point, Mumbai. And the secretary of J.N. Tata, Padamsha, and Diwan Sheshadri Iyer, and the Mysore Samsthana had a very close connection with Swami Vivekananda, and Sister Nivedita played a big role. And this noble lady said, you can take as much land as you want. And at that point in time, the Mysore king was only 9 years old. And in fact, some of you have visited the Krishnarajasagar Dam in Mysore. This great queen pledged her jewelry to the Sahukars of Mudigundam, which is another small town close to my native place. And by the money that she got by pledging the jewelry, she actually completed the Krishnarajasagar Dam. So it's a very interesting, fascinating story, so that in IASC, several legends have lived, including C.V. Raman. Of course, I am very fond of Professor Satish Dhawan, mainly because ISRO has had a wonderful connection with him. Several systems that you really see in IASC today is all because of the wonderful work done by both C.V. Raman as well as, Satish Dhawanji. But I always wondered, basic science is more like Brahma. Now the new information, new thing always emerges out of Brahmadeva according to the ancient Indian mythology. But then you don't find too many temples for Brahma. Probably in, I think Jaipur, there is a temple, maybe in one or two places, because society never recognizes science. Because society cannot see new information in totality just as the way scientists see. So in basic science, we always ask a question why and try to understand the nature and try our journey. But then engineering has been little bit more fashionable like the Vishnu. You will find umpteen number of temples for Vishnu. And it's all kinds of avatar, not just the Dashavatar, but then you have your recent avatars in Swiggy and so many other places because engineers go all over the place today. While science asks the question why, maybe engineers ask the question why not. But technology is more like Shiva, where you don't really ask any questions because the day a technology is born, it is bound to die. No, but then this is very, very, enigmatic kind of a scenario. As scientist, do I work in basic science? Do I do engineering? Do I do technology? But I would simply say we should do research for the sheer joy of finding the answer to the unknown. But of course, nowadays we all suffer from the P raised to the power of n syndrome. We are worried about number of PhDs we produce, number of publications, promotion, project. I think this list is endless. The only return on investment for a scientist, as I feel, is that sheer joy that I get when I find answers to that unknown question. And it is better start enjoying this because when you are between 20 to 40, you have all the time, you have all the energy, but then you have no money, including funding is a problem, family is a problem. So when you are young, this is a very diabolical situation. Between maybe 40 to 60, you have all the money, you have all the energy, but you have no time. After 60, I think you have all the time and all the money, but then you have no energy. So it's very important for us to recognize that we should enjoy. And what I'm going to tell you a little story is how the shockwave got hitched on to us and how this entire journey has been so very enjoyable. But before I go forward, this one lady has been phenomenally influential on my own life. I'm sure many of you would have read her stories and autobiography. If you have not done, I would urge you to go back and read Madame Curie, mainly because of one particular reason. Even today, if you go to France, they don't allow you to step into our grave beyond 20 seconds because they believe radioactivity is still there in that particular grave. And this lady took all her patents in the name of humanity. That service to humanity, which Ramakrishna Mission talks about, Atmano Mokshartham Jagatshitaya. Probably I saw in this particular lady's life that even today Mary Curie Foundation has funded thousands of students for their doctoral program and postdoctoral program. I think we should never have fear of perfection, but we should always strive hard to serve the humanity in totality. It all began in the 1970s. I am sure some of you would recognize Professor Reddy here and Professor Arunan, but I don't know how many of you know this particular gentleman, Professor N.M. Reddy. In fact, I was the last giant student of Professor N.M. Reddy and KPJ Reddy. And when he returned from University of Toronto in the 1970s, he was a student of Professor Dhawan. He was specially invited by Dhawan to come back to India, and after finishing his PhD with the illustrious Irwin Israel Glass, who is actually regarded as the father of shockwave. He worked in NASA and then he came back and he probably set up this India's first shock tunnel. Of course, at that point in time, these facilities played a very big role in SLV3 and many other things. Of course, today, before I go into say what actually we do, I also want to tell you a little bit of history about shockwave itself. Some of you may be surprised that it was a mathematician by name Benjamin Robbins who actually coined and showed to the world there is a wave phenomena called shockwave. And he was the one in 1746 who actually managed to do experiments with a ballistic pendulum. He was able to measure the actual speed at Mach 1.5 at 20 degrees. This is probably the first projectile which was moving at about 500 meters per second or so. Today, of course, we know that as the velocity of the vehicle increases, the problem is that the drag is going to go as the square root of velocity, whereas the heat transfer goes as the cubic root of velocity. So this velocity increasing leads to actual drag was one of the early inventions where people started looking at shock waves more carefully. Then Ernst Mach was another scientist who did quite a bit of work. But in a layman's term, to me, the definition of shock wave is slightly different. In fact, I still remember that wonderful lecture Dr. Bharadwaj gave during our recently held shockwave symposium, where he was able to show intergalactic shockwaves which are traveling at 50 kilometers per second. It's phenomenal. But in a terrestrial, circumstances, shockwaves are usually very strong perturbations that are created in air in aerodynamics. They do propagate at velocities which are virtually independent of the wave amplitude. In fact, you could also define them slightly differently. You can say whenever large amount of energy needs to be dissipated in a very short time, shock waves are one of the most preferred forms of energy dissipation in nature. In nature, it could be an explosion, it could be a new star being born, or it could be merging of galaxies, or a nuclear explosion. Whenever large amount of energy needs to be dissipated in a very, very short time, these are the only means by which you could do that. But for layman, you could also say what happens when a shock wave travels through a medium? It actually instantaneously increases both pressure and temperature of the medium. When I say instantaneously, this is the only known wave phenomena which is hardly of a thickness of few angstroms, which can increase the temperature within few microseconds to something like, say, 4,000 degrees centigrade. It can also increase the pressure to hundreds of bar, and then it can come down drastically in an exponential manner. How do you play around with this energy is what has actually shaped the destiny of several research groups around the world. I just show you here the plot between pressure versus time. You could very clearly say that the area under the curve would actually indicate the impulse, and how do you play around with this impulse can actually do wonderful things. And in fact, we have shown that you can even put a DNA inside a cell, or you can break a rock using this energy. It is all in your hands. How do you really handle this energy? But of course, for aerospace people, this has been more as a poetic justice. This is one of the photographs that my friend in NASA took several years ago when the bomber actually flew at a supersonic Mach number. For aerospace engineers, I want to know what is the distance between the wave and the body, because this region is going to be under very high temperature and pressure. I need to adopt thermal protection system. So this is true with all your re-entry vehicles, large vehicle nose cones, space recovery, experimental modules, reusable launch vehicles, missiles. So as aerospace engineers, we don't want shock interactions on the body. We don't want local hotspot. We want them to go out and be as away from the body as possible. People also talk about how do you ensure the body to be very, kind of blunt, so that you have a fixed region where you know what is the heat transfer and things like that. But in reality, of course, you will find plenty of opportunities to look at shock waves, including a cannon being fired from a ship. You will see the reflection of a shock wave on the water body itself, or the sonic boom experiment that most of you would be aware, or the stars merging in the outer galaxy. PRL has been the cradle of space science. I think a lot of work would have gone on in these areas. But I'll also tell you something very interesting. This is not something you will only find in the terrestrial life or in the outer space. In fact, if you go below, maybe say 1 or 2 kilometers below the sea, there is a shrimp called pistol shrimp. And the name itself is very interesting. It is called pistol shrimp because it has two claws here, and it actually moves the claws at such tremendous speed. The water that is there in between the claw virtually evaporates, creating a cavitation bubble. And when the cavitation bubble ruptures, it actually creates a shock wave. And the sound generated by the shrimp is so hard, many of the submariners, when they move around, they mistake this to be somebody shooting underwater. That's why the name pistol shrimp. People in Denmark and a couple of universities have actually put a shrimp in a wind tunnel. They have visualized in a water tunnel, and they have actually visualized the cavitation bubble rupture and measured using a needle hydrophone the shock wave profile. So the message is the shock waves are there everywhere, friends. So it is not something which is exclusive of aerospace or someone else, but then they could be quite deadly. So what is it that we did in IAC for the last several years is to understand the science associated with shock waves. How does it propagate in different media? Can we really use some engineering solutions to understand these things? Maybe at the end of the day, come out with some kind of a technology. In fact, the pistol shrimp uses shock wave to prey. The shock generated out of the cavitation bubble virtually makes sure that the other fish or any creature ahead of that freezes. We should remember that blast waves have a component called infrasonic between 18 hertz to almost close to 28 hertz. Whenever we hear a very good music, we all feel goosebump, because the human body also has got a lot of infrasonic content. Now, how do you really play around with this infrasonic content is also another separate area of research, which is gathering a lot of interest in the recent time. This is the view of our small lab that we have in Indian Institute of Science. This is about 2,230 square meters. But of course, incidentally, this is also the largest lab of its kind in a university setup anywhere in the world. We are very proud of this lab because it is students over the last quarter century who have built many facilities. Even Bala was with us where he looked at a lot of work on the chemical kinetics at some point in time before he moved on to PRL. So you will find several facilities here like shock tubes, shock tunnel, chemical shock tubes, vertical shock tubes, all kinds of facilities are here. Any student who comes in actually builds his own facility. And luckily in Bangalore, we have a very good infrastructure of the surrounding industries and the small scale industries, they have been able to support us tremendously. But the good news is while we build facilities for our own research, I watch my word, this I feel is a very important component of technology development. If you don't build the equipment for your own research, I don't think we will be able to build any technology in this country. Fundamental science progressed because Sir C.V. Raman built his own spectrometer. I am sure Dr. Bharadwaj and several of you in PRL have that wonderful culture starting from Vikram Sarabhai to build facilities for your own research. You're not thriving on borrowed facilities from abroad. Yes, we do borrow maybe a couple of diagnostic tools which is not available, but then the culture of building facility is what we wanted to showcase. And today we have exported shock tubes to United States of America. And in fact, in University of Texas, they use the shock tube built by us for their teaching program. University of Mississippi, they use a shock tube for structural research. South Korea uses a shock tube for the research, again built and developed in Bangalore. You feel really very happy about India because Atmanirbharata comes when you want to showcase these technologies to rest of the world. Of course, we were not like this many years ago when we began, and I think, forgive me if I just become little nostalgic. I still remember it was way back in 95 when Dr. Kalam used to visit IAC very often. These facilities, we do experiments for about 1 millisecond, which is 1,000th of a second, which is very hard for anybody to even visualize because even when I do like this, it is more than a second. And at that point in time, he said, show me a shock wave, and I will believe that these kind of experiments can be done in these facilities. Unfortunately, we never had big money. In fact, our initial experiments, started with some of the money from PF, which Professor Reddy put, and some money I ended up contributing. A couple of good people who were there. We all pulled in about 50,000. We struck an electric discharge between a model and a needle, which was there in the free stream. We photographed this discharge in the night because we couldn't afford electronics to do electronic switching. But believe me, when I first got this shockwave picture, after a struggle of about 6 months, it actually created a lot of buzz in the country. People believed, yes, you can do experiments in a shock tunnel when you have the hypersonic flow only for about few milliseconds. In 2012, when Dr. Kalam visited to inaugurate our Center of Excellence, I showed him this particular movie. I hope you were able to watch. The entire flow development in a shock tunnel we were able to see with a high-speed camera and a Schlieren setup. This high-speed camera at that point in time was about 45 lakh rupees. And what we spent for these single shot photograph was about 45,000 rupees. Yes, money does matter, but money should not actually stop you from pursuing science. That fire in the belly or the urge to know the unknown, actually what drives science. And this was probably the first eureka moment that we have in the lab. Of course, later on today, we are able to even visualize Kalpana Chawla's accident kind of a scenario where the re-entry flow can be done. There are only about 7 labs in the world who can do this. We can virtually do a spectroscopy of how different lines of, the heart plasma gets developed on re-entry bodies can be done in the lab, which is actually a big step forward for India to really understand most of the programs in these areas. So we have asked several big questions over the last couple of years to really understand both hypersonic flow as well as shock waves in totality. That is the reason why we merged 3 laboratories which were there in the previous premises. The lab on chemical kinetics with Professor Arunan started, the high enthalpy laboratory which was originally started by N.M. Reddy, later on was given wonderful shape by Professor K.P.J. Reddy. And when I came back from Japan and joined as a faculty in IAC, I started a shockwave laboratory. We believed that we should actually break the silos. We joined all of them and called it as Laboratory for Hypersonic and Shockwave Research. So all that we do here corresponds to how hypersonic aerothermodynamics can be understood in its totality. How do we really properly reduce drag? How do you really understand the hypersonic flow transition? At the same time, since shockwave is central to the entire gambit of activities, how do you really understand the energy that can be carried out by shockwave when it is propagating in composite media? So these answers to these large questions led to several interesting problems. Hypersonics in any case has become extremely important in the last few years, at least in the last 2 years, people have been talking about hypersonics to a large extent, mainly because the defense applications have taken precedence. For example, anywhere in the world in 1.5 hours is the mantra of many of the countries. Today, countries like China and Russia, they do claim they have built hypersonic missile. India also has embarked on a very big program in this area. And incidentally, the largest hypersonic meet, the AAA conference on space planes and hypersonic, is being hosted by IASC incidentally in the month of May, where the scientists from around the world would congregate to really take stock of what is happening in this entire area. Normally, people talk about a missile without an engine here, where they do a ground launch, and these kind of very novel shapes allows the liberty for these vehicles to glide in the outer atmosphere and then come down at anybody's command. No radar can actually detect any of these hypersonic gliders or hypersonic cruisers. In fact, if you look at the several programs that are there, still we do not have a successful scramjet engine, supersonic jet engine. And this is one engine which does not have any rotating parts. So everybody is trying to chase this technology. In fact, it is said whoever masters this scramjet engine will rule the world for next 300 years. So this is a very important area where America has invested heavily. In fact, last year, the US budget on hypersonic was $4.2 billion. It's a very large amount of money where multiple institutions are working. Of course, you may be surprised that hypersonics is no longer the job of defense people. There is a startup company in Europe, and this is called Destinus. And this is an artistic view of their hypersonic plane, which they are building for transport of cargo. They want to travel at Mach 12 times the speed of sound, and they promise delivery of goods anywhere in the world within 24 hours. And they raised about $50 million last month. So the whole spectrum is changing where a lot of private players are coming into commercial operations in hypersonic in addition to our own, say, defense needs. There are several activities in LHSR, the Laboratory for Hypersonic and Shockwave Research. But what would be common in all of this is to understand what is the difference and the interaction between the flow kinematic effect and the flow energetic effect. How does the interplay really alter the aerodynamics over the body? How do fluids mix? Can I really measure the temperature in the presence of a shock wave? What does plasma do to the entire flow field? So several questions like this is what is usually ask. And we spend all our time in understanding the fascinating world of shock wave and hypersonic flow, as well as in supersonic flow. Recognizing the important work, BrahMos Aerospace started a center of excellence in 2010, 2011, and we have scientists from BrahMos who work with us very closely in IASC. Here we have been able to do a lot of system design activities. We are able to do multi-design optimization, trying to build a supersonic optically accessible combustion test rig, build systems, and now many of the findings have joined hands, and the India's program on hypersonics also has taken off. I'll just give you some glimpses of very important technical problems that one needs to understand the fundamental flow physics. The flow, when the Reynolds number becomes very large, there is a transition which takes place from laminar to turbulent. In hypersonic flow, this transition is a very, very important parameter because when the flow becomes turbulent, the aerodynamic drag shoots up non-linearly, the surface heat transfer shoots up non-linearly, so you can't really control the vehicle. When you have a hypersonic vehicle with a scramjet engine, you want a combustion chamber where there is no rotating part, the flow to be turbulent so that mixing is better. How do you really fix the transition point is again another big area of research. So during COVID, because we found a very good student, Ankit, who decided to stay back, we spent all our time and then we were able to demonstrate for the first time in the world that in a shock tunnel, you will be able to do some wonderful experiments on transition. The small gauges that you see here, these are all platinum thin film gauges which were built in-house, where we are able to measure the heat transfer rate on these bodies like cones and elliptic cones. And large number of these are all platinum thin films which are fired on a Mechar substrate. Mechar is what is called as a machinable glass, so that no heat basically goes into the surface. And then in all these facilities, we end up getting a test time of about couple of milliseconds. But within that millisecond, you can actually understand and capture very clearly what is the phenomena associated with transition. In fact, for the first time, we have been able to capture the jump in heat transfer in laminar, transitional, and the turbulent boundary layer. Now, these are very important data for designers. So using this, you can actually really decide what part of the body should be laminar flow and what part of the body should be turbulent flow. In fact, we have also artificially tried to trip the boundary layer, and instead of the conventional trips, which are nothing but protuberances over the surface, we now believe that cavity means a small depression, appears to be more effective in terms of boundary layer transition. We also measure what is called as an intermittency for the first time. This is the first such measurement which is yet to be published, where we are able to figure out the high frequency content that is there in a transitional or a turbulent boundary layer. Incidentally, Professor Narasimha, who is no more, he came out with this so-called classical S curve for subsonic flow way back in the 1950s. When what was holding good for subsonic flow, for the first time we are seeing the universal intermittency curve also holds good for hypersonic flow. In fact, when he was alive, he was always pushing us to investigate hypersonic flow transition. Probably this is only poetic justice that these results came out only after his demise. But then this is testimony to his foresight in the 1950s, where he talked about a universal intermittency curve. Of course, we also look at unsteadiness associated with shock-induced separation in a big way, because these are all fundamental phenomena which are typical of any hypersonic machine. For us, it is important to understand not only the frequency content, but we also should get what is the impact of the shock frequency on the actual frequency associated with this wave. You may remember a couple of years ago, the transonic shock, actually we lost a launch vehicle in one of the launches where the transonic shock came and interacted with the shroud shock, creating a local hotspot where the entire temperature rise was so large, drag was so huge, it created a pitching moment where the launch vehicle had to go down. So the understanding the unsteadiness induced separation is a very important part, and this is something which we do routinely. We also did something on fundamental chemistry, because engineers always think basic physics, chemistry is not really important. But then this is one such case where Professor Aruna and Professor Reddy, we all joined many years ago. If you just put a chromium coating on a blunt vehicle, the natural heat that is there in the hypersonic flow will allow the chromium to evaporate, And that exothermic reaction of chromium will basically push the shock away from the body, bringing down the drag by 40%. So you don't need to really do anything except to put a small chromium coating over missile or a launch vehicle head. You can actually look at bringing down the drag substantially so that you can use lesser fuel, or for the same fuel, you can basically go to a longer distance. So these are very exciting experiments where exothermic chromium reaction with atomic oxygen can actually be used for something wonderfully well in the hypersonic flow. Of course, we have looked at the unstart phenomena, which has become extremely critical now in the development of scramjet engine. And this has resulted in a problem of many of the flight tests actually failing because the shock unsteadiness reaches a certain time. And at some point in time, it starts oscillating and the whole flow basically comes out and the fuel does not really burn. In an ideal case, in a scramjet engine, the region behind the shock where the temperatures are very high, you usually inject the fuel and the fuel burns instantaneously out of auto ignition. Understanding this throttling induced unstart is something which we did very recently. So we have a very nice facility in the Indian Institute of Science where we have built our own scramjet engine. We are also trying to understand how does supersonic flow mix, how do they really burn, can we really understand any of these? We are now asking to really build India's own scramjet engine, which would be useful in many applications. In fact, ISRO started off many years ago with hydrogen, and they also flight tested one such case along with Lazar was there when Dr. Lazar and even JDA Subramaniam was, of course, he retired in BSSC. Several years ago, he built a direct connect mode test facility. But now they are also coming and trying to do this using hydrocarbon as a fuel. How does the chemical kinetics of hydrocarbon affect supersonic combustion is a separate area of research where quite a bit of work is happening even in IIT. So many of the important things here that I want to highlight is the chemistry plays such an important role in scramjet combustion. In fact, Chinese have now embarked on building a new facility called expansion tunnel, where they can generate turbulent chemistry in the laboratory because they found in flight test they are not able to understand the role played by soot formation and turbulent chemistry. And ignition delay is a very important parameter. This is something which, thanks to Professor Arunan, which he began the work in IASC many years ago when there were no programs on hypersonics in this country. Today, using a shock tube, you can actually measure the ignition delay. How quickly will it burn? How quickly the pyrolysis takes place? What are the products of equilibrium chemistry? How do I really take the radicals and do a GCMS and come back and give them the number of reactions that actually form the final heat release process in a scramjet engine? As engineers, we want the number of steps that a hydrocarbon fuel, say like JP7 undergoes. What is the total amount of heat? What are the radicals that I should avoid so that there is no soot formation? Because India is now embarking on a very long duration hypersonic flight close to 700 seconds. It is important for us to understand some of these fundamental phenomena. Chemistry plays a very major role, and I think this is also the facility where Dr. Bala spent considerable amount of time and contributed immensely to the development of this area of research when he was there in IAC. Of course, nowadays they are also thinking of using the same fuel to cool the scramjet engine, so that they are all called as endothermic fuel, which means the fuel entering the engine is at a higher temperature. That means the fuel is actually cracked fuel. If the fuel is cracked, then what happens to the efficiency of pyrolysis process? What kind of radicals come out? What is the role played by PAH in the soot formation? These are all questions what normally kinetics people used to talk in conventional chemistry. They're all becoming very important in supersonic combustion now. Well, this is about aerospace, which has been my own passion for last several years. Next 15-20 minutes, I will show you that shock waves are not just in aerospace, but in virtually several areas. Thanks to Dr. Janardhan Raj, who actually drew up this tree when he worked for his PhD with me several years ago, you would see virtually almost everything has been covered in this particular tree of shock waves. starting from application to earth science, astronomy, to biology, to chemical engineering, to wood science, agriculture, material science, you name it. Today, there are more than 18 different faculty from 8 different departments in IASU who use our laboratory. And this is here we asked a question whether shock wave is a move or is it a bane? Because a shock from an explosion can actually kill a person. And during Diwali days, you have a cracker, and if the pressure is anything over and above 0.7 bar, it can rupture the lungs. Shocks are deadly. In fact, the trauma-induced brain injury that you see in soldiers who are returning from battlefield is a very serious area of research. But we thought, can we move away from aerospace to look at something totally interesting? Because we need to understand blast certainly from the defense perspective to put mine protection boots or even the protected bulletproof jackets and things like that. And we also looked at several unusual applications in the lab. For example, even a landmine simulator can be done in the laboratory using shockwave. This is one such experiment. We completely recreated a small landmine in a safe manner. And once by looking at the particle distribution, you can actually understand how shock gets attenuated in sand. This is a very important area of research because speed of sound in sand is 280 meters per second. In air, it is about 330 meters per second. Does the shock reflect the same way in sand surface as the conventional air or the solid surface? So these are all some of the things which made us work in this area. In fact, you would see sandbags being used in airport to attenuate shock waves whenever the bullet penetration and all. But unfortunately, in India, for the geographical location, we don't even have a standard which measures the attenuation coefficient in sand. So for the first time, along with DRDO laboratory, we embarked on taking different sand samples in different parts of the India, strategic location, because they build underground bunkers to store ammunition. And whenever you store, you need to understand how quickly a given thickness of the sand attenuates shock wave. Shock tubes are one of the very nice ways of creating explosions without using explosives in a safe manner. We can recreate the entire Freelander profile in the lab. So right now we are in the process of putting what is called as a grain map for the entire country so that the bunkers can be built in a more efficient manner. We now know how sand particles basically absorb the shock energy. How do they really attenuate? This is where I said science plays such a big role in all of them. Of course, you need to come out with different kinds of laboratory simulators. I'm actually showing some of the very recent work where we have built a tabletop system where I can generate a very large time. For me, large time means tens of milliseconds, not conventional seconds. So here in the lab, we can generate using liquid, maybe water on one side and air on another side, a blast wave whose profile, the decay time is of the order of about 120 milliseconds. This facility is now drawn a lot of attention, and we would be using it to understand how blast waves interact on marine structure. This is another recent one where we have been able to build a water-based shock tube where you can read very large pressure, so the order of close to about 1 GPa in a very safe manner on a small scale metal sample. In fact, we are trying to understand, for example, how high strain rate affects magnesium. Magnesium is a very interesting kind of a material. Right now, along with Professor Satyam Suhas, we are using magnesium alloys which are invariably used for both automotive industry as well as aerospace. What happens to the fundamental texture? Does the crystal structure change under high strain rate? These are some very basic questions that we are addressing using these facilities. All these days, we could not do such experiments because we did not have a facility, but now we do have such things. In fact, shock-induced deformation has shown new type of grain refinement that is taking place. In fact, the strength seems to increase with shock deformation. So maybe shock waves could be used for something very useful even in material science in the years to come. Of course, sometimes we wonder in academic institutes, why do they put us in so many committees? In fact, one such committee was a student advisory committee where I met Professor Deepshika Chakravarti maybe several years ago. And while the committee activities can take place, we said, I have a device where I can inject vaccine. Can you actually understand the biology and do some animal trials? In fact, that is how my own work in biology started, today we have produced a couple of PhDs, and I'll show you some very interesting results which have come out. In fact, here using shock waves, we are able to do needleless drug delivery. In fact, this is a system which we have patented and animal trials are over. And we have been very clearly able to show that vaccine delivery can be comfortably done to targeted Langerhans cell below the skin, which absorbs the vaccine. And then they can move around comfortably, and the amount of vaccine you need is actually 1/10 of what you do with the needle route. This we need to commercialize and start the human trials, which we would be doing shortly. In fact, we ended up building some very unusual devices. In fact, here we use solar energy and we use a small electrolysis, and we burn the mixture of hydrogen oxygen to create a very nice shock wave. And these are all very tiny electrolyzers that we have built, using which you can actually inject a DNA inside a cell. For the first time we showed you can actually do cell transformation using shock waves. And these are very complicated cells like mycobacterium, agrobacterium, which cannot be transformed by conventional means because biologists would like to put a DNA inside a cell. So we were able to do this using shock waves. In fact, this is something very interesting that happened over a period of time. And I never thought one day as a mechanical engineer, I will start measuring the Young's modulus of the E. coli bacteria subjected to shock wave. Because E. coli is so tiny, it's not even a micron. But surprisingly, to our dismay, we found out that this can withstand 120 bar of overpressure. It's not a small value, for about 80 to 100 microsecond. And it actually elongates. And this we measured for the first time, where we saw a bacteria which is usually like this becomes elongated upon exposure to shock wave of a particular strength. And after that, it comes back to its original part. In fact, this was one of the thought processes which led us into looking at angiogenesis much later in an endothelial cell, which resulted in some very interesting applications about which I will brief you shortly. But as an aerospace engineer, I never thought one day I will put a mice inside a shock tube, because we thought that we should understand trauma-induced brain injury and our own response to immune system. So this is a conventional shock tube, and if you expose these animals to certain dosage of shock wave, they find that their immune protection is basically improving. Today, I am tying with an idea that I would build a shock generator which would be there in every clinic. When a patient enters the clinic, he will get a low dose of shock, which ruptures the biofilm, allowing the antibiotics to act better. I never thought, after all, shock waves are also useful. So you don't have to worry about killing a person, but you can actually play around. In fact, animal trials have shown shock waves actually induce immunoprotection against salmonella in mice model. Like you expose them to certain shock wave and then challenge them with salmonella. The shock wave treated solution, the animals, they perform much better. There's a very interesting biological pathway called one of the P5 protein route, which is actually giving that additional immunoprotection to these animals. Of course, I have talked about several applications here, but I just want to deviate a little bit on the technology, because most of us believe that Lakshmi and Saraswati cannot reside in the same house. The old dogmatic Hindu view is that if you study, you will not make money, but if you make money, you won't study. But I beg to differ. I think if we have to build technologies, both Lakshmi and Saraswati should reside together. A professor should never be called as a poor professor. We should at some point in time make an attempt to take our science to the common man, and we should not be allergic in making money to showcase to the next generation. After all, pure pursuit of knowledge also pays. That's why I normally believe in what I call as a D4 model for innovation. We should dream, design, deliver, and make done, or dollars. So with this, maybe somewhere in 2011, both me and Professor Reddy, we thought we would take a look at startups, and we built our own industry. And over the last 10 years, we haven't made much money, but then we haven't lost money either. We have been able to create some very interesting products which are now in the market and slowly helping people. But I'll tell you about one particular product, why I called this particular Vyakhyaan as Healing Touch. And this is a device which is now being used for actually treating wounds in diabetic patients. I never thought when I began the exercise 25 years ago, one day I will build a miniature device, I will produce a shock wave, and then that shock wave will be able to heal the wound in a diabetic patient. Now, this is a device which is now almost commercial. The emergency clinical trials are now going on. But it started off with a very fundamental question of what happens to endothelial cell when we expose them to shock. To our surprise, we found that these endothelial cells actually showed angiogenesis, where new blood vessels are formed. It also showed a particular release of P38 protein. It also showed avalanche of calcium and cell proliferation. With that particular background, having understood the science along with our own biology colleagues, we thought we will do some punch biopsy wounds in animal. To our dismay, within 15 days, this entire few deep wound in mice actually disappeared. It actually closed without any medicine. That is when we found that there is a natural healing because of angiogenesis that takes place in wound. We said we will patent this and then look at these things in much more closely in science. Under a microscope, we actually looked at the cell proliferation, and the uncontrolled one, there is no healing. But then if you have the shockwave treated, you can actually see how the gap closes very quickly. So we patented all of this, and we said we found an investor, and we also started the clinical trials. Please don't take any photograph, but what actually filled my heart with joy was very recently when I went and saw some of the patients. In fact, there was a biology teacher who was superannuated from one of the schools in a remote part of Karnataka, whose had no leg. He had an amputated boot. And then this particular device beautifully healed that. And when I came out, the joy and the tears in the face of their family made me feel, yes, my life is done. At least about 12 patients have been now completely healed. And it's a very simple device to operate. This is what I meant by society doesn't recognize angiogenesis, but it wants their pain to be alleviated. I'm so happy that shockwave has today really become a proper healing test. You can see that those wounds are very bad. Then they actually start healing those areas. Type 1 diabetic patients. We are now extending this to burn wounds. But I was more careful about frostbite because soldiers in the battlefield have frostbite. So we did some experiment of liquid nitrogen induced frostbite, and very beautifully the shockwave basically heals even these wounds. So we are very excited. Hopefully by the end of this year, we should be able to do a larger trial and then perhaps make it commercial, which we will do, so that it also fetches for itself. We also did several such exercises. I'll just show you some glimpses. In fact, we had some exercise on using lab to land is not very easy. Technology is not very easy. We still work in progress. The good thing is I gave the key which was fitted with chocolate or honorable investor. He remarked, "I say हमारा बहुत बड़ा मौका है." We have also done something similar to bamboo in Nagpur, where we have installed a big plant where round bamboos can be treated using shockwaves. And preservative impregnation in bamboos is very difficult by conventional method. So this is also something which we are trying to commercialize now. This is also some very interesting chemistry. Again, we used hydrogen oxygen and created a very strong shockwave of the order of about 2,500 bar. And then we ended up building the entire shock tube and used it for oil fracking below the ground with a project from ONGC. This is a technology which is about 80% complete now, where we are able to frack shale rocks to bring out oil. And we have completely eliminated the need for water. So these are very exciting times where I have put a shockwave below the ground. I also have the first version handheld, which can actually heal a wound. And that is the beauty of this wave. It can kill a person, but if you use them properly, there are very interesting applications of the shock. In fact, very recently, we built a very big shock tube, which is incidentally the largest shock tube of its kind in the country, 500 diameter in Sifis in DRDO, where they will use this facility to design better bunkers for our soldiers. Concrete panels, you can actually test them and do a digital image correlation. to understand the basic physics. I very firmly believe basic physics and applied mathematics is what engineering is all about. So it is in this context, I think these kind of exercises are very important. But I have learned one thing very simple in my own life. We need to break the silos if we want to do anything big in terms of technology. Unless we work together, and this is a culture which ISRO completely, in many sense, started many years ago with the help of Vikram Sarabhai ji and then many others. But I think even academic institutions should start working with the industry, layman, common society, because if you don't become relevant to society, I don't think our own life really becomes meaningful. But one thing is very clear, friends, at the end of this journey, I can very fondly say that if I want to conclude in one sentence, what have you done in 25 years? I have actually realized how stupid I am. Nature humbles you. We thought we knew several things about shock waves, but after 25 years, I have just remained stupid. But if you remain stupid, you will ask questions. If you ask questions, you will find answers. Those answers would actually become something useful to the society. As the small Kannada phrase that I have put here, which only means that you can actually become a jewel which the nation never forgets you because you have solved its problem. Paramahamsa very beautifully put it, as long as I live, so long do I learn, is what Swami Paramahamsa said. And I think this Amrut Vyakhyaan, for me, the take home is, it's such a wonderful concept that you actually called people from several cross sections to share their ideas. Science should become beneficial to the society. As long as the common man does not understand what we are doing, in my view, that is no science at all. And you need to remain stupid and really inquisitive throughout your life to ask those questions, to understand the unresolved mystery of this wonderful nature. I once again thank the director PRL for giving me that wonderful opportunity to share some of my ideas. Maybe I was a little bit at hypersonic speed trying to cover too many things in this talk. But I thought I'll just give you a glimpse of what we have been doing. Yes, we take pride in remaining stupid in the area of shockwave because that is going to keep us going for the next maybe several decades. Thank you very much, sir. I would be very happy to take any questions.
Thank you, Professor Jagdish. I would like to invite our colleague, Dr. Avik, to take up the question session.
Thank you, Professor Jagdish.
Shall I stop sharing?
You may need actually to answer the question. Is there any question from the audience? From Webex?
So Bharadwaj has a question. He has raised his hand.
Okay. Yes, Professor Bharadwaj.
Thank you, Professor Jagdish, for a very exciting talk, covering so vast areas, starting from aerospace to aircraft to launch vehicle to astronomy to space science to biology, human medical science, and then to agriculture, tea, oil industry, and wound healing and things like that. So it was really a very, very fascinating talk, enlightening us about how to utilize our own knowledge for society. So science and society, two sides of the same coin, is what you have demonstrated. A very nice talk. So my question to you is that you have been worked for so long now in this field. Do you still think that there are certain processes which we still don't understand?
You are very right. In fact, the energy absorption mechanism of shock wave with a single mammalian cell, for example, we don't understand. Or for I keep a steel plate and expose that to shock wave, how does the energy alter the fundamental crystal structure? We don't understand. In fact, when we began some of the work with metallurgists, we all know that the material will deform. But the deform is fine, there is no recrystallization. But then when we did the actual microstructure analysis, we found a new crystal orientation has shown up in the material. Why is it showing up? We have no clue. Or for example, under very high shock wave pressure, the whole field becomes plasma, the boundary layer becomes chemically reacting. We have absolutely no clue of how the chemically reacting boundary layer affects the aerodynamic drag. Or, for example, the chemistry associated with the supersonic combustion. What is the role played by shock-induced chemistry in the release of polyaromatic halogens? We have no clue. I think there are so many questions which would probably keep us alive for the next 100 years.
Rightly said so. Rightly said so. So what I understand from now from your talk is that this shock science, I should say, is really multidisciplinary, and you can actually utilize shock in a controlled fashion to make it really boon for the society. And it can actually be applied in various domains of science, right from metallurgy to material science to your human biology to agriculture science to geoscience to space science, astronomy, everywhere. But my question still is, I'm trying to understand, do we have any mathematical formulations where we really say that most of our physics which we understand can be actually put into mathematical terms?
You're very right. I did not touch that part here. The Navier-Stokes equations are reasonably well defined for understanding many of these things. But the problem is, full Navier-Stokes equation cannot be solved because we have not understood enough about turbulence. On the solid mechanics side, we know about the Rankine-Hubelite, the relationship that exists between the change in pressure to change in volume. But then we have simply no idea on the new equation of state for several materials that are actually used. So mathematical modeling has matured reasonably well over the last 50 years. Today, many of these things that I showed here are things which cannot be done on the modeling, which needs experiment. And based on the experiment, you can do better modeling. For example, in our own work on hypersonic flow transition, we wrote our own implicit large eddy simulation tool to really see how the mixing shear layer breaks down. How do they really merge? Or on the material front, now we are trying to get a new way to understand the equation of state of a novel material, which are now proposed as bulletproof jackets or things like that. Yes, mathematics is understood, but then it is a partial differential equation, system of partial differential equation, which cannot be solved because we don't know the boundary conditions. But they can go hand in hand. And I think advancement has to happen on the analytical solutions, experiments, flight trials, and also mathematics. They go hand in hand.
Great. Thank you. Thank you. Over to you, Avik.
Any further question? RT, please.
Yeah. Thank you very much for such a nice talk. I wanted to know, like you showed that shock waves are useful for wound healing. So what is the physical, chemical and biological process for this healing? Whether it is understood or just like you put the shock waves and it does the healing?
That's a very interesting question. I just briefly touched upon it, but then I did not want to talk too much of biology because I myself do not know too much of biology. We spent about 4.5 years to really understand how does the endothelial cell react when it is exposed to a certain dose of shock. So our initial experiments were basically on a petri dish where we grew colonies of endothelial cell. And then very quickly we understood that there are certain biological and chemical pathways that are triggered. One of them is when the shock's energy is absorbed by the cell, the angiogenesis happens. Angiogenesis is broadly a term given for more blood flow. So in the vicinity, surprisingly, the sizes are becoming more in endothelial cell wall. Angiogenesis is promoted because of shock. And what promotes angiogenesis is because of three different routes. One is there is a protein called P38. And that protein, when it gets activated, it triggers series of biochemical reactions inside, which leads to larger angiogenesis, cell proliferation, leading to wound healing. And it releases nitrous oxide as well as calcium. So any calcium release will also lead to more angiogenesis. So only when we understood this part of the science then a stray thought occurred whether we could use it for a wound healing of all kinds. But diabetic wound healing was more prevalent because India is a diabetic capital, lot of amputations. So we thought, can we try regular wound healing? That is how we ended up doing experiments on animals. So this has taken us almost about close to 6 years before we were able to use it on humans. We have understood I wouldn't say that all the pathways are understood, but all the prominent pathways that are required to ensure the efficacy, non-toxicity, safe nature of these devices. Because the zone of influence of the shockwave, if you see, is not even 5 millimeter.
Yeah.
So you have a small diaphragm which creates a shock, and the shock will be felt by the wound only in an area of 5 millimeter up to a depth of about 1 mm. So if you have a larger wound, you need to move it around.
Yeah.
But if you ask how many shots are enough in a patient, in fact, in some patients, they had to take it almost up to 70 days because they were type 1 diabetic and they had no sensation in the foot at all. And the wounds were basically very deep. But we saw beautifully angiogenesis resulting in new tissues being formed and the wound naturally healing. So the biophysics is reasonably well understood. Doctors also subscribe to these 3 prominent pathways, but we continue that work because there would be several. Human body is so complicated.
Yeah.
Maybe it something else in the near future.
Thank you. Thank you very much.
Any further question? Professor Raju, please.
Yes. Am I audible?
Yeah.
Okay. Thank you for this fascinating talk. A lot of applications, a lot of new things that I learned today. Couple of questions I have. One is in terms of the E. coli that you mentioned. It expanded and contracted after the shock process. Is that process why it happens? Is it known? And the second question is in terms of do we understand the reason for production of various enzymes due to shocks? Various P32, you said it's produced. How is it produced due to shocks? So these are the couple of questions that I have.
That's a very interesting question, yeah, because in E. coli, the first experiment that we did was, suppose say you have a shock peak pressure of about 100 bar, which lasts for about 120 microseconds. The cell walls were expanding. It's like a membrane pores. Anyway, the membranes are porous because E. coli doesn't really have any subcellular organisms. It just expanded. And when it expanded, we were able to put a naked plasmid DNA inside that. But these expansion process, the entire molecular biophysics is not completely understood. We simply do not know why is it expanding. And more than anything, it expands for about half an hour and then it comes back to its original place. So when we measured the Young's modulus, this looks like a very fine elastic behavior. But then if the pressure pulse of same 100 bar, I keep it for a slightly longer duration, something like say 150 microsecond, then it dies. So the cell rupture takes place. And the release of certain enzymes, we have found 1 or 2 pathways we have identified. But then the correct answer is, if there is a protein unfolding that is taking place, what is happening to nucleotides inside because of shock, how the energy is absorbed. It again boils down to that fundamental question that I raised. We simply have no clue on what is the amount of energy absorbed, what is the nature of this process, which is so short, because this itself is lesser than the inertial time scale. Because many of these bacterial experiments are done in time scales of 100 microseconds, which is ridiculously small. But then the material is able to absorb. For example, we have done some experiments on rabbit bones. If you have a fracture, after exposure to shock, it is healing much quicker. Cracks are closing. But again, we don't know why this is happening. So we need to understand, this is a huge area of research where a lot more biochemists have to come in to understand the molecular level interaction. So the answer at this point in time is, we know we are only scratching on the surface.
This brings me to another point, and that is if if healing is faster, means some reactions are happening very rapidly because the calcium is getting produced at a faster rate. So that is the thing that we are observing. So you're able to say that it is healing. But what are the other things that may be happening rapidly, which we are not observing, which may have some other consequences? Is also
This is a very important question. In fact, we went through this quite a long time. The good thing is the pulse that we really create in many of these wound healing is very short. It is not something which is about 100 microseconds. It's a very small pulse, highly localized pulse. This is not something the whole body generates. Again, calcium avalanche is not something as soon as I give a shock, there is an avalanche. No, it actually takes quite a bit of time. In fact, it takes about, say, few days. It's not like I give a shock, immediately it comes. And the cell closure, the wound closure, which is typically due to cell proliferation, that also doesn't happen instantaneously. So body takes some time to react, and these series of reaction pathways that I showed you, at this point in time, they have not really shown to have any long-term repercussions because the energy is very ridiculously low, highly focused at a point. But yes, the question is whether it would lead into a new DNA signature. These are all things which we ourselves are asking and continuing the work. But doctors feel that the wound healing is taking place because of not some medication. The angiogenesis is a very natural phenomena in the body. And we are only promoting that, which actually is very useful. New blood vessels forming is a fantastic indicator. If there were to be something dangerous, obviously angiogenesis would not take place. So the very fact that angiogenesis is happening consistently for a given shock strength gives us a lot of hope.
Thank you very much, Professor Jagadeesh, for this fascinating talk and this interaction. Thank you.
Any further question? Navinder, if you want to ask. Nandita?
So I had a question about this again in the same line which others are asking. On what factors does your intensity of the shock wave that you are utilizing for healing and other, applications depends? And how do you decide? For example, you said it took, if I remember correctly, it took about 70 days in some cases to heal the wound. So how do you decide what is the intensity? If it can be, the frequency can be reduced or increased to get the healing done in quickly or something. So that
Okay,
is
so
what.
this is a question which I don't decide, doctors decide, number one.
Okay.
Secondly, the area under the curve, then when you take, it has a broad frequency spectrum. So there is also a infrasonic, there is a megahertz frequency, all of them are there. But what the wound or a human body would see is the entire energy in totality in a very small place. In fact, this is nothing new. You would have heard about extracorporeal lithotripsy, where kidney stones are removed using shock waves without any surgery. But then those shocks are so strong, they have to break the wound. And the entire medical industry is in some sense monopolized by people who build those electroporators, the devices, lithotripsers. So no other new devices basically came in. Whereas we wanted to break this, and we started off in understanding the propagation of shock, energy absorption in biological media, how viscosity affects this, how the cell actually absorbs the energy. So these work that you see here is not something where we did some hit and miss and all. It all started as a basic curiosity question. But the wound healing mechanism, there are standard parameters clinicians have. Every day they monitor several biochemical, tests they do. They also monitor the size of the wound. And why 70 days in some cases is when they are type 1 diabetic, the healing is virtually non-existent. In fact, they were showing me a patient where there was almost a gangrene in the feet, but then the patient did not even feel the pain because they call it as a neuropathy, where all the nerve endings, they stop. Only when it started smelling, she found out something was wrong in her feet. Now, such kind of wound, if you want to heal, one of the condition is we can't use this device if the wound is completely dry. That is what happens in gangrene, because the diabetic wound is a complicated thing. A lot of endocrinology is also associated with that. And when it becomes dry, shockwave would be useless because thermodynamics doesn't work. I need some fluid where the energy can be absorbed. So these actually shocks usually propagate the slowest in air, little faster in liquid, fastest in solids. So the thumb rule in all of this is, yes, in the beginning, it has to evolve. What could be the dosage? The number of days and number of shots per day, and nowadays the clinicians say alternate days are good enough, sir, because we are not finding any big change between daily and alternate day after about 2 weeks. So it's a multiple process now. Doctors have gone into the, they are more knowledgeable. And biology is also, we are also now trying to look at the gene sequencing. We are picking up that is the purpose of clinical trial 1 and 2. So by the end of this year, we would have a larger population. We will also look at the gene sequencing, like what Chakravarti pointed out, that whether there are any new DNA that is cropping up because of this exposure over a long period. So these are all questions which is still work in progress.
Thank you. Thank you very much, Professor Jagadeesh.
Question from anybody? I'll take this opportunity to ask one question. And okay, I'm an astrophysicist, and in astrophysics, what we see is that a big role of Rayleigh-Taylor instability at the shock front. So in your experiment, say for example in magnetosphere, Earth's magnetosphere, also we see Rayleigh-Taylor instability is getting developed at the shock front. So in your experiment, do you see, or can you resolve that part so much that you see the instability structures? And in aerodynamics, how that turbulence generated because of the Rayleigh-Taylor instability plays a role?
This is a very important part that you mentioned. So in fact, we look at a couple of instabilities even in aerodynamics. One is the Kelvin-Helmholtz instability is what we usually see when the shear layer breaks up and start mixing with the outer fluid. Now in the astrophysical flow, it is a lot more complicated. Whereas here we may have at some time, for example, in the picture that you are simply seeing on supersonic mixing, we are only having a supersonic flow which is actually entraining, and then you have the presence of shock cell and the flow becomes turbulent downstream. Many of these things we have Rayleigh flow instability, Kelvin-Helmholtz instability. We also have Geutler vortices which are mostly formed in, we usually in hypersonic turbulent flow, we call it as a second mode, where there is a large second frequency which is of the order of hundreds of kilohertz which shows up in the flow field. We also have Rittmeyer-Meshkov instability whenever there is a cylindrical shock wave which happens, because that is something which is very closely associated with nuclear fusion and cylindrical shock waves collapsing. I have not shown some of the results here, although we don't do much work now. I have done some collaborative work on Rittmeyer-Meshkov instability in cylindrical shock tubes. But again, in laboratory experiments are no way an ideal replica of astrophysical flow, because there the energy levels are very large. Magnetic field complicates the scenario. The Reynolds number and the Mach numbers are way above what we can normally talk in conventional aerodynamic flow. In fact, we cannot even use Navier-Stokes equation in many of those formulations to approximate. But yes, we are looking at instabilities, like mostly Kelvin-Helmholtz holds good up to supersonic. After that, we end up looking at only Geutler vortices formation. But still the shear layer, mixing shear layer evolution and the strong shocks, even in aerodynamics, is not fully understood. For example, if I have a chemical reaction and it releases locally heat, then the interplay between the linear stability theory basically breaks down. So the linear stability theory which people use, or the hydrodynamic stability theory, none of them work at higher enthalpies. In fact, the impact of shocks with, say, a projectile penetrating, this is an experiment which we did for the International Space Station many years ago. A projectile penetrates through, say, a multi-bumper Whipple shields. The bigger projectile becomes smaller and smaller. But then when the projectile goes there, it is no longer hydrodynamics. The whole metal behaves like a fluid. There are adiabatic shear bands which are formed. So the instability itself is entirely, in fact, even Rittmeyer-Meshkov instability invariably we will have at least 10 to 20 papers in our International Shockwave Symposium even now. So it's not a very well understood phenomena, but it is definitely there, but we can correlate both.
But Richtmeier-Meshkov, do you see in these kind of shocks, Richtmeier-Meshkov?
Yes. In laboratory cases, we do see, and we can have an analogous shock in converging cylindrical shock wave. We can actually see Richtmeier-Meshkov.
Okay, because we say that for it is an MHD shock basically. That's MHD instability because of the magnetic field. So, but in hydrodynamic shock also you have some analogy closer to that.
Yes.
Okay. Okay. Thank you very much. Any further question? Okay, I'll again further ask you another question regarding. Okay, RP, please.
Yeah, just wanted to know whether this molecular and atomic spectroscopy has been done under the influence of shocks.
Say that again, molecular?
A molecular and atomic spectroscopy under the influence of shock has been done, like simultaneous observation of spectroscopy.
No, sir. Simultaneous was a little difficult. This is actually one dream experiment we want to do. Now we are in a position to build miniature shock generators. While you are looking at microscope, you can give a shock. Most of the E. coli work that we did was we fixed the cell after giving shock and then took it under the microscope, because many of these conventional microscopes are with so limited access. So you can't actually. This is one dream experiment we also thought we should do when we put a DNA inside, because I want to see the opening of the cell wall where the porosity increased and the DNA went inside. So we may need some good innovative engineering solutions or an endoscopic shock generator, which does not disturb the surrounding area, and then look at this. This has not been done till date.
Oh, thank you.
In lasers, the Don Knott, who is there in Illinois Institute of University Urbana-Champaign, he has done something on femtosecond and nanoshocks through chemical molecules. So not in the biological sense, but there again, they are looking at laser intensity. So they use one more laser to figure out the shock front, and then from there they get back to equation of state and all. But we have not really looked at, say, a single cell till date.
Okay, thank you.
Okay, if there is no more question, then probably I'll. Is there any question from web? If there is no, then I'll hand it over to Dr. Vineet Goswami for vote of thanks. Thank you, Professor Jagadeesh, for a nice talk, nice answers as well.
Thank you very much.
Yeah, thank you very much, Dr. Avid Sarkar. So this brings us to the conclusion of the 79th episode of PRL Amrut Vyakhyaan. So at first, I would like to thank and express my gratitude and heartily thank Professor Gopalan Jagadeesh for accepting our invitation and giving an excellent colloquium on the topic of shocking waves, healing touch in PRL Amrut Vyakhyaan. I would also like to thank Professor Jagadeesh for answering the audience's questions. Next, I would like to thank our audiences on both the YouTube and WebEx platforms. I would now like to express my sincere thanks to PRL Director, Professor Anil Bhardwaj, Dean PRL, Professor D. Palam Raju, and Chair of the PRL Amrut Vyakhyaan Committee, Professor Nandita Shrivastava, for all their support in organizing this episode of PRL Amrut Vyakhyaan successfully. I also thank my colleagues in Vyakhyaan Organizing Committee for successfully conducting today's episode of PRL Amrut Vyakhyaan series. I sincerely thank you all for being part of the Azadi Ka Amrit Mahotsav and PRL at 75 celebrations. Kindly do visit our website and other media platforms to know more about the other events at PRL, in particular the current event, this event, PRL Amrut Vyakhyaan. And with these words, I would like to propose for the closure of today's episode of PRL Amrut Vyakhyaan. Thank you very much.